Good afternoon. We're going to go over section 15.1, which is about pH. We have a new definition for acids and bases. We were using the Arrhenius definition, which just says acids give off hydrogen, bases give off hydroxide. This one is a little more specific. It is acids are proton donors. A proton is another way of saying H+, because a hydrogen atom is just one proton surrounded by one electron, and when it's positively charged, you've lost that electron. All you're left with is the proton in the center. Okay, the positive little proton in the middle. A base is going to be a proton acceptor. So this is very different than the Arrhenius one. We're not saying that it gives off H, but it has accepted an H+. Okay. So example, looking at this HCl, I can see the chloride over here has lost its H. It has donated that H to the water and become H3O+. So this is still our acid. So either definition works for that one. I'm going to go ahead and talk about ammonia, even though it's not on here. So separate example, NH3 is going to react with water in a very different way. The NH3 looks like this in its Lewis structure. It has this negative part, it's polar like water, and it will participate in hydrogen bonding like water. And when you mix it with water, I have H2O, H and H. One of these hydrogens will be more attracted to the nitrogen, and some of them will come off, leaving the OH behind. Okay, it is going to be a weak base, so not very many of the waters will do that, but some of them will, leaving OH behind. So when the H joins the NH3, it becomes NH4+. The proton has gone from the water to the ammonium, and what's left is your OH, which is negatively charged. So ammonia, NH3, is a base, a weak base. Okay, so now water by itself in a container, we have a beaker of water. It is going to ionize all on its own. Okay, it's self-ionization of water. The water is going to break down. If I have two water molecules, then one of them, so I have water and another water right here. One of them can lose a hydrogen to the other water molecule. And if it does that, I will get OH- right here. If this hydrogen joins that one, I will get H3O+ here, and OH- will be left over here. That is self-ionization. It doesn't happen very often, but it does happen. It happens so infrequently, though, that the concentration of these things, H3O+ and OH-, we have measured at 25 degrees over and over again, and the concentration is 1 × 10⁻⁷ moles per liter. So only 0.000001 moles of this per liter of solution is going to ionize. Okay, pH calculations. So a reminder that the brackets that we will see in this section mean concentration in molarity. So we're talking about the concentrations of hydronium or hydrogen. Remember, H+ and H3O+ are going to be equivalent values. The hydroxide concentration looks like that. Okay. So for the ionization of water, we have a K, which is a constant with a little W for water. This is the ionization constant of water, KW, ionization constant of water. And because the concentration of OH- and H3O+, they have to be equal, because every one of these that loses, this one gains. So these are going to be in equal amounts. It's two of these, but this is a 1-to-1 ratio over here, 1 H3O+ to 1 hydroxide. The concentration of each of them is going to be that value. So if I plug in 1 × 10⁻⁷ times 1 × 10⁻⁷, I will get this value right here. And so KW is always that number. So when you see kW, you're going to plug in that number, 1 times 10 to the negative 14th. Okay, so that makes an equation that we can use to solve problems. If I know kW is always this value, and I know either of these, then I can use my algebra to find the missing one. So sample problem A, 1 times 10 to the negative 5th molar of HNO3 was prepared. Calculate H3O plus, this is a two-part question. Well, H3O plus is the amount of H plus, and this is a sneaky way of telling you that HNO3 is a strong acid. You have to know those strong acids to be able to do the problem. So if I put in 1 times 10 to the negative 5th moles per liter of this HNO3, I'm going to get 1.0 times 10 to the negative 5th moles per liter of H plus, and 1.0 times 10 to the negative 5 moles per liter of NO3 minus, but we don't care about that, NO3 minus. So the H3O plus is going to be our starting concentration. HNO3 is a strong acid. It ionizes completely. So HNO3 is going to give off H plus. That H plus is going to combine with the water to give us H3O plus, so it's just the given number. Okay, second part. Now we want to find how much hydroxide was in there. We're going to use this equation. So plug in our Kw. That is, I'll rewrite it over here. 1 times 10 to the negative 14 is Kw. And that is equal to H3O plus that we just found. 1 times 10 to the negative 5. And our OH is what we are looking for. You can call it X if you want and solve for the X. To solve it, we're going to divide both sides by our H3O plus. Divide. These cancel. That divided by that, well, this is an algebra problem. Negative 14 minus negative 5 is going to be negative 9. So 1 times 10, you can only do that when the number in front is 1. By the way, for the other ones that get a little harder, we're going to need our calculators. Okay, so this is just a reminder of what we already said. Concentration is in molarity, that's moles of solute. The solute, the things that are dissolving that we care about in this problem is H plus or OH minus over the liters of our total solution, so total liters of solution, okay? Go ahead and try these practice problems. I don't have them, so I'm not going to do them here, but you can look up the answers in your book. Try those problems.